Yes. Hello, everyone. My name is Henrik Andersson. I'm here. And this is a work that I joint work with another professor at my department at the Norwegian University of Science and Technology up north in Trondheim. And we also have two students. It was basically the students who did most of the work, and me and Marielle who helped them, you can say. So this is a math heuristic for a multi-product inventory routing problem. The outline is like this. I will start by presenting the problem so that you know what we are talking about. Then I will say something about the literature, what has been done in this area. I will not show you the mathematical formulation, but I will discuss it, and also some valid inequalities that we have used to strengthen it. Then the core of the presentation is the math heuristic that consists of a construction phase and an improvement phase. And I will go through those two. And then I will show you some results in the computational study and conclude. So the problem description. Usually when we talk about maritime inventory routing problems or inventory routing problems in general, we say that it's basically two problems in one. You have a routing part and you have an inventory part. And now in this case we have added a third component, which is basically how to handle the bulk products on board the ship. So first we have ship routing and scheduling as one part. We look at the short sea shipping problem, which means that the time spent in port is relatively large compared with the sailing times. We have a heterogeneous fleet of ships, so each ship is different from another one. Even if they are identical, they usually start at different places at sea. So there are a heterogeneous fleet. Then when it comes to the load and inventory management, we have multiple products, and they are produced and consumed in each port. So one port can be a production port for one product and a consumption port for another. And then the next port, there are different products that are produced and consumed. There are, of course, limited inventory and ship capacities, so we cannot take as much as we want always. And it's also possible to handle multiple products during one port visit. So we visit a port and we can unload some of the goods that we, or some of the products that we have, and then we can load other products. And the third component, so this is basically the standard inventory routing part of the problem. Then we have also the allocation of product to compartments. So we see each ship as a number of compartments with different capacities, and we see the products as multiple and unmixable. So we cannot have two different products in the same compartment at the same time. So each ship has a heterogeneous set of compartments. We have not done so much about them. They can have different classes where you can put some chemicals in one, but you cannot do it in another. We have made it a bit simpler, so we just say that basically the compartment has a capacity and it can store that much of any product. And we use something called undedicated compartments. So a compartment can have product A on the first leg, then we unload this product, we load product B in the same compartment to the next port, and so on. So here is a small picture of a solution to the problem. There are 4 ports. We see, for example, here in port 4, there are 3 different products. The green and the pink are produced here. So we see that the production rate makes the inventory level go up. Then there is, I think, we can say that the blue vessel comes first here. It loads some of the green and some of the pink, and then continues, while a bit later the yellow, or yeah, let's call it yellow, comes to this port and loads more of the pink and unloads the yellow. So this is what happens in port 4. This is port 1, 2, and 3, and so on. And we see that the ship, for example, this ship sails starting in port 1, go to port 3 to 4 and 2, and then to an artificial end node, which is basically anywhere. If we look at it from the ship side, we have here a ship starting with 3 compartments, one with a yellow product, or orange is probably better, and 2 blue. Then it enters the first port, it unloads the light blue, it continues, it loads more of the orange, it continues, it loads more of the orange into the same compartment, and it loads the yellow one here, and continues and continues. So depending on if we look at it from a port side or from a ship side, the problem looks quite different. So what has been done on this problem prior to this study? I will not go through everything that has been written on maritime inventory routing, but we'll have picked some of the multi-product papers that has been written and just mention how they handle the allocation on board. And the most common thing is to have no handling of the products. We say the ship has this capacity, we can load it with any products we want, and we can mix them however we want. Of course, then we overestimate how much we can actually transport, because if we have these compartments, we have to be sure that we fill one and not start on the next one, because then that one will be occupied. A second line of research has to do with dedicated compartments. Then we basically say that compartment number 1 on this ship can only contain apple juice, compartment 2 can only contain this product and this product and this product, and so on. And then the problem becomes quite a lot easier, because then you don't have to decide where to put the product. When you come to a port, you know that the ship has 2 compartments for the product you want to load, and you load these compartments. And then the last thing is to have these undedicated compartments. When you can switch product in a compartment, there can only be one product at a time, but you can have different products after one another. And then we have only found one paper so far that has worked on this, Sisvanto et al. They have a structure where they have a loading region where they load different products, and then they go to an unloading region where they unload all the products and then basically go empty back. I think it's different types of oil or petrochemical products. And then they have undedicated compartments, but they make sure that the ship is always empty when they return, and then they can start to refill it again with different products. So it's a little bit of cheating, but okay in this case, because they really use the geography of the problem to handle this. And then, of course, it's our study, which is on undedicated compartments. So the formulation, we use something called a time discrete formulation. So each port appears in the network at each point in time. So we have port number 2 on day 1, day 2, day 3, and so on. And then a path through this network describes how the ship moves. So this ship starts somewhere, it sails to port 2, then it waits for 1 day or 1 time period, then it operates, which basically means that it can either load or unload or do both. Then it continues to port 1, where it operates 1 time period, and then it sails to port 4, where it operates 1 time period. And the reason for having these time discrete formulations is that we then can have a time-varying production and consumption rates. So we can say in port 1, day 1, we produce 13 of this product. The next day we produce 10. The third day we produce 7, and so on. While if we have a constant rates, then you can it's easier to model it differently. But here we use a time-discrete formulation. To do this, we need some constraints and some variables. So starting with the routing constraints, we need some form of start and end conditions for the vessels. We know where it starts. We know that it will go to some kind of artificial end node at the end. We need flow conservation. So if a ship enters a port in a given day, it must leave that port the same day, either sailing or waiting or operating. We make sure that there are no waiting after an operation. So once we finish operating, we have to sail. And then if we want to wait, we can wait before we start operating in the next port. And we also make sure that we must operate in a port before we continue sailing. We cannot just go to the port and wait and then continue. And there are some berth capacity constraints specifying how many ships can operate in one port at the same time. And then, yeah, for these we have routing variables saying if we sail from I to J starting at time T with vessel V, operating variables if we operate in this time period in this port, and waiting variables, which is basically the same, but waiting instead. Then, of course, we need to take care of the load management and allocation. And this, when you try to explain mathematical models, it sounds sometimes a bit strange because it's so obvious for us, but in mathematics it's not. So we can only load or unload during operation. Of course, why should we do something else? But the mathematical model doesn't know that this is that it's only allowed to load or unload during the operation. Then we, of course, need some load balance constraints on board the ship so that we make sure that we don't create products, so products just don't disappear. We can only have one product in each compartment, and we have the compartment capacity. And for this, we have some loading variables. How much is it on board ship V in compartment C of product K at time period T? We have load and unloading variables that are connected to this one. And we have allocation variables that says if product K is in compartment C of vessel V in time T. Last but not least, we have the inventory constraints at the ports. So here is port I and port J. So we need some kind of inventory balance, which is updated every day with the consumption or production that we know, and is updated when we unload and load from the ship. We have the capacity at each inventory, and we have some kind of initial inventory constraint. And for this, we need some kind of inventory level variable. And then we mix all this together into a nice model, try to solve it. It's not a very good model, it's weak. So we add some valid inequalities. And then it's always hard to come up with good valid inequalities. But what we have done is that if we take a product that is produced in a given port, it starts at an initial level, and then the amount in the inventory increases with time until it reaches some kind of upper inventory level. And then if we don't do anything, it continues to increase. So then we can define something that we call excess production of this product, and the same thing down here, excess consumption. So this is the least amount of this product that we have to remove or load from this port. If we load this much onto the ship, we will, at the end of the time horizon, reach the upper limit exactly. If we take more, then we will end up somewhere below. But this is the least amount that we have to pick up in this port. And then if we sum over all products that have excess production and compare that with all products that have excess consumption and take the max of these, Then we know how much in total we have to either remove from the port or add to the port. And then we can divide that by the capacity, the capacity of the largest ship, and then we get some kind of minimum number of port visits. So if this term becomes 1.5, we know that we need at least 2 ships to this port. Of course, we can make this a little stronger by doing some nice tricks down here, but I don't explain that here. We can then use the same, this excess production, and divide it by the capacity of a compartment, the largest capacity of a compartment, and there we get how many compartments do we need to take to this port. So either we take the production or the consumption and divide. And the last thing is we take this term, the total amount, so we sum both excess production and excess consumption. We sum this over all products. That is the least amount of product that we have to operate, either load or unload, and then we can divide that by the port capacity per time unit, and we get then the minimum number of operation periods. So this might say that we need to have a ship operating in this port at least 7 days in a 6-week period or so. So these constraints can be added a priori to the model, and it increases the bound quite a lot. We can also look at time. So here, if we have a production port, the initial inventory, it goes up to the upper inventory level. Then we know that the first visit to this port must be somewhere in this time interval. So then we can say that a ship must visit this port inside this time interval. If we don't have this, you usually have a fraction of a ship visiting at different times, and it does not necessarily sum up to 1 here. We can also look from the end. We assume that we have a full inventory at the last day of the time period, and then we see when, if we don't do anything, when is the first time that we, let's see, so that I say, have I used the wrong figure here? Let's skip that one now. Yeah. That was the model. It's hard to solve. It takes a long time. So instead we tried to be a little more clever and came up with a Matheuristic, which is basically a heuristic method that uses this mathematical formulation as a major part of it. So, as I said, the exact solution method is inefficient, but we see that we have different components in the formulation that is kind of not so very linked. So it's low interdependence between the routing and the load and the inventory part. So if we could first find routes, then given these routes, we can check, is it possible to have feasible inventory levels and levels on board the ships so that we can sail and perform everything without the inventories going over full or empty. So therefore we split the problem in two, one routing part and one inventory management part. So this is basically the flow in the Matheuristic. We initialize a routing problem. I will discuss that later. We solve it. Then we take the sequence of port visits that we have. We relax them a little in time, and we solve an inventory problem, giving these fixed routes, and we solve it with soft inventory limits. And then we check, are we within the real inventory limits when we have solved this problem? If yes, then we have a feasible solution and we go to an improvement phase. If not, then we can identify where are the infeasibilities, and we can try to change the routing problem in a way so that we get a new routing solution that is hopefully better when we come back here. So the construction phase, to create a feasible solution, we have the routing problem. Then we only have basically routing variables and some, I call them operation variables. Here it doesn't matter if it's operation or waiting, it's just that we have to stay in a port for a given number of days. We have the same routing constraints as in the original model, and we add all these valid inequalities, which all has to do with the number of times you have to visit a port. And then we can get a solution like this. It's not an easy problem, even though we have removed everything that has to do with products, but it basically says that, yeah, port 3 has to be visited twice, maybe one time in this time period, the second time in this time period, and so on. And we try to fulfill that as cheap as possible. Then we take the routing solution and we formulate something called a hop-indexed formulation, which basically makes sure that each leg in the route is sailed in the same sequence as in the solution from the routing problem. And then we also add this binary variable saying if we break an inventory limit or not. And then we can get something like this. So this is 2 ships, and the length of these rectangles show how many days they stay in each port. And then given the solution for the blue port, for the blue ship, saying we have to visit port 1, and then 2, and then 3, and then 1, and then 4. We can kind of decide in the inventory problem how many days we stay at each port in order to load what we want. But of course, given these 2 routes, or not of course, but in this case, we have a breach over here. So if we take port 2, we see that we have a long visit by the blue ship in the beginning. So the inventory started here, it went down, the blue ship came and unloaded, then we continued to consume, the orange ship came and unloaded, and then no more ship came. So here we went under the real lower inventory level, and we are still within the limit of the soft lower inventory, but here we have an infeasibility or a violation. And then we can record that, oh, it happened in time 29 and time 30. And then we can take that information and try to translate that into something that we can change the routing problem with. And then we have tried 4 different strategies in doing this. The first one is to see, oh, here is a violation. A violation, then we know which port it's in, which product it's the violation is, or which inventory it is, and at what time. And then we basically look at the product. So this is the violation port of this product. It's this consumption port. Then we take all production ports of that product and say that we have to have at least 1 extra arc from these ports to this one before this time. So we enforce that we have to sail from these ports to this port. This is a rather strong enforcement. The next strategy is to basically see how many times, how many operation periods do we have before the violation in the iteration before this one, and then we add a few extra. We say, oh, we need 2 more. And then we say we have to have this many operation periods in this port in the new iteration. Of course, neither of these make sure that we get a feasible solution, but hopefully it changes the routing in such a way that we at least get closer to a feasible solution. The third strategy, then we take, I would say it's a mild version of enforcing an arc. So we basically take the violation port where it happens, and then if this is a consumption port, we create a super source which will send 1 unit of goods from this port to this violation port through the production ports of this product. And this will hopefully, since we have to send 1 unit either this way or this way, we have to kind of create more flow from these source ports to this violation port. But we don't need to have a direct connection. So we could, for example, let this extra unit go through this production port to a port that neither produce nor consume this product, and down to the violation port, if that is the best thing to do. And then the last strategy, then we just say that we don't want the same route as or the same route solution as we already had. So then we change the X, or we add a hop index formulation to the routing problem as well, and basically say that we have to make at least 1 change to the solution that we have. And hopefully when we iterate this, we get to a feasible solution. It's not necessary, but it's nice. And then we can take this solution, it might be good, it might be bad, and try to improve it. And that we can do either by doing intra-route improvement or inter-route improvement. And in the intra-route improvement, we take 1 route at a time, and we basically see how many times does this route visit port 1, port 3, and port 2. And then we basically take this route out of the solution, and we say that this ship that sails this schedule can have this no more than the same number of visits to each port than in this schedule. So we can reduce the number of visits, but we cannot add visits in this case. And then it's possible to change the sequence and doing other things with the solution. So this is done for each ship. Then the other way we try to improve the solution is to take a number of time periods, and then we basically say that everything within this in this time period is open. We can do whatever we want, but we have to make sure that we kind of hit the solution that we have outside. Here we allow some slack in the operations, because it might be quite hard to have an operation exactly here when we start changing things inside here. So we allow, for example, this to be 1 day before or 1 day after. And then we solve this problem on a much smaller time period than the original one. And if we get an improvement, we try to do this again and then this again until we don't find any improving solutions. We have done a computational study. We have 3 different cases, a small one. You see here, it's not the really big problems that we can solve, but for maritime inventory routing problems, this is usually the sizes that we are working with. So the small one has 2 ships, 4 ports, and 3 products. The medium is a bit bigger, and the large is even bigger than that. And we solve it over 42 time periods, which I think in this case is either 6 weeks or 2 weeks with 8 hours intervals. We have created 5 small instances, 4 mediums and 4 large. we have solved the exact the exact formulation. We have used different strategies. So in the greedy, we only use strategy 1, that is enforcing arcs. In valid, we use the milder ones, 2, 3, and 4. And in hybrid, we use 2 and 3, and if the strategy 2 and 3, and if that doesn't work, we go to the greedy one. And what we can see here, we have collected the average solution, the average time it took to solve the instances, and the average gap. And for the small instance, we can solve all of them to optimality with the exact formulation. Only using the construction phase, we get a gap here of, between 4 and 6%. But we see, when we take the overall, that the greedy is quite fast and gives a decent result, while the valid one is not so fast, but gives a better gap. So there is a trade-off here. And both of them are better than the exact formulation. If we add the improvement phase as well, so taking the feasible solution that we have and trying to improve it, we have reduced the number of instances, and we have only tested combinations of intra and inter operators here. Then we can see that the gap becomes almost 0 in the small instance case. And now that the greedy algorithm seems to work best, both time-wise and average gap-wise. And I think that we have an explanation for this. That is that when we use the greedy operator, we add arcs. So we add 4 more visits than it's actually needed. And then when we take the improvement phase, we are allowed to remove visits. We are not allowed to include extra visits, but we are allowed to remove. So therefore, when we have the greedy, we have a better, even though the solution might not be better in real, it's better for the improvement phase because the improvement phase has more to work with. So, concluding remarks. We have a time discrete formulation for this problem, and we have a Matheuristic to solve it. And in this case, it seems that the greedy strategy actually works best with regard to both solution time and quality. Okay. Thank you very much. I think I ran over time, so should we say questions for later?
Part-time window with
yeah.
But anyway, anybody have a question for him?
Yes.
Just a very quick one. When you have compartments on a vessel, you really also should look at the hydrostatic part. If you, for instance, fill the compartments at the very ends of the vessel, the bending moment for sure will be too high.
Yeah.
So I think there are some simple box-formed limits you can put on this, but because it's a capacity just like all your other capacities, and not that difficult to model.
Yeah. Yeah, there are a lot of things we can do with the compartments. We have washing either, that you might need some time when you go from one product to the other because you have to clean the compartment, but we have disregarded that. The problem is already too hard to solve.
I have a question from an environmental perspective. These solutions are likely to be environment friendly in the sense that they minimize fuel consumption or emissions. Can you say something about this?
Yeah, I think I can take David's words that when we do this kind of more clever, we save, we make them more green because we use, maybe we can save one ship or we can save a few port visits and so on. It's also possible in here, since we have this time discrete formulation, to have different sailing speeds and say if I want to go fast, I it takes 4 days, and it will generate this much CO2. If I say it'll slower, it will take 6 days, and it will take that. It's no problem to add that to the model. So, yeah, it's half green now. But, yeah. Okay.